Hello, good morning. We will start our study today. Starting today, we will work on chapter 8 and chapter 9. I have told you to watch lecture video from last week. Okay. And those are just to remind you that the lecture video the one you watch should be from announcement 5, lesson 11 and lesson 12. Let's see where you can find it on the announcement. Maybe I use student view. So in the announcement 5, watch lesson up to test 4, and you should watch lesson 11, starting from the 1 hour 43rd. Okay, basically start from hypothesis testing. In this lesson 11, I explain the structure of hypothesis testing. And in lesson 12, I did problems regarding hypothesis testing for one parameter. That's chapter 8. Now, next week, we will do hypothesis testing on 2 parameters. Now, when I record the lecture video for lesson 13, it gets cut off. So I think at that time, we have some kind of like power outage or Canvas suddenly down or Zoom suddenly down. I don't remember what happened. So what happened was then my video was cut into 2 pieces. So you need to watch these 2 before next week. Okay. Now, the one I need you to watch before today's lesson, you need to have watched lesson 11 starting from 1:43 minute, 1 hour 43rd minute, and then also watch lesson 12. Okay. At least you have watched lesson 11. At least you have watched lesson 11, this one here. Don't proceed until you watch this. Okay, it will confuse you even more. Okay, now lesson 12, basically I went over problems in one of my handout. Today I have another handout. Okay, I have another handout for 1. Now then 2, 3, 4, which come from 8.3, 8.2, and 8.4, I will do problems from our textbook. Okay, now just to remind ourselves that the template or the structure that you always need to use when you do hypothesis testing. Okay, the first one, the claim. Second, hypothesis, which is followed by null hypothesis, alternate hypothesis with colon, and you put braces here. Okay, now for the hypothesis, you will have parameters, either mu or p or sigma squared or sigma. That's in the first part here, followed by either either equal to or less than equal to or greater than equal to a number. Okay, the alternate hypothesis must not have equal sign, and it should be the complement of what we have in null hypothesis. So if the null hypothesis equal sign, this is not equal sign. If the null hypothesis less than equal to, then it will be greater than. If the null hypothesis greater equals to, then it will be less than. Okay, now most of the time, however, the claim has something to do, most of the time, not all the time, but most of the time, the claim has inequality that does not have equal sign. Now then you decide the alternate hypothesis first, then you do the null hypothesis. Okay, that could be the case. That could be the case. But the structure will be as that following. Okay, null hypothesis will be the ones that have equal sign. Alternate hypothesis does not have equal sign. Now the third step, we will do test statistic. Okay, test statistic will be C score when we do, this is X bar minus mu over sigma over square root of n. That's if we are testing mu with sigma unknown. We'll use T score when we are testing mu with sigma unknown. Don't worry, we'll do that again later on when we deal with the problems. Okay, and then we'll use C score P hat minus P over square root of PQ over N. That's when we are testing P. And it will be chi squared degree of freedom minus sample variance over population variance when we are testing sigma squared. And then, you know what, let me write it this way. Give me a second. I will reorganize this. That's our template. Step 1, 2, 3, and then step 4. Continue step 4 here is P value. Now, if you want extra credit, then we will also do the critical value. And then after that, we do informal conclusion, which is if the P value greater than alpha, fail to reject null hypothesis, if the P value is less than alpha, actually the rules actually greater or equals to alpha, fail to reject null hypothesis, less than alpha will reject null hypothesis. Now, if we use critical value method, traditional method, the rules will be the informal conclusion. So both of them actually informal conclusion. If the test statistic in the tail, then we'll reject null hypothesis. Otherwise, fail to reject null hypothesis. Okay, and then step 6, conclusion. Now, in my introduction, lesson 11, I gave the details, what is claim. So I don't want to answer that question here. Thomas, how do I know what is claim? No, that's the question we already answered at that time. There's no need for me to repeat it. If I need to repeat everything again, then we don't have enough time for examples, right? Okay. What you don't want to happen is like, I need to do everything all over again every time I have a new student coming to class. No need. Okay. So the lecture video is already there. Okay. What I do right now is providing you examples. Okay. So please watch that first. Okay. And how about hypothesis, Thomas? What is that actually? You know, in the past, I have that kind of question. You know, in the past, I have that kind of questions like, Thomas, what is hypothesis? And I ask that person, have you watched the video? And that person say, no, I don't have time for this. So, well, what makes you think I have time to answer your silly questions? Okay, I mean, I say that it was silly because like that's a question he could easily find the answer if he would just spend time watching the video instead of just bombard me with questions. You know, I mean, I don't mind answering questions, but do your part, and then I clarify what is not clear. Okay, so the question I expect was question like this. Okay, Thomas, according to the passage, I read this, and that's the claim. Therefore, we are the same with the claim, but my hypothesis will be this because this is my interpretation. Now, that's the kind of question I would like to have. Okay, or Thomas, I think the wording says that the wording implies that the population standard deviation is unknown. Therefore, we're supposed to use this formula instead of this formula. Now, bring up those kind of questions. Okay. Of course, if it's just little questions, Thomas, can you remind me again, why is this, why is that? And of course, I don't mind. But if you ask me to explain all over again everything, why we have to do these 6 steps, I explained that in my lecture video. Okay, yeah, but there are actually many steps. Okay, some teachers actually break it into 4 steps. That's the very, very minimum though. 4 steps basically combining step 1 and 2 in one step, and then step 3 as their step 2, and then they don't have informal conclusion. They just go to conclusion right away. Now, some other teachers, they have 8 steps. Other textbook have 9 steps. Okay, but when we actually write hypothesis testing report, I'm talking about report, what you actually need to show when you perform hypothesis testing and write the report formally, then you have to write these 6 steps. So I'm teaching you how to look professional here. Okay, I'm teaching you how to look professional regardless what you know. Thomas, can I skip to step 4? Well, I can skip to step 4 too. But when you write a report, okay, what will you write? This is what I want. Okay, so in your test later on, when you answer my hypothesis testing question, you write it as if you are writing a report. Okay, now you will see that once you get used to it and you see more and more variation of problems, then you will see why we need these six steps. Okay, why we need 6 steps. What you don't want to happen is this though. One common mistake that happened in the past, if people don't learn statistics, they don't realize this, is the following. They make one claim here. But the conclusion has nothing to do with the claim. That's really, really bad. Okay. Now, for example, I just make up stories. Okay. For example, but I mean, you saw this before. You saw this before last year. We see that a lot. The claim, the current president is not a good president. He's not supposed to be re-elected. Right? Okay, and then they did hypothesis testing, a lot of full analysis. The conclusion, then we need to elect. You need to vote for the other guy. No, the claim is not that. The claim was about the current president at that time. So the conclusion should be about that current president. Okay, the fact that we're supposed to vote for somebody else, that requires another hypothesis testing. Okay. Now I'm not saying that I'm in support of the previous president. I mean the president in 2020. No, that's not what I'm saying. It's just like a bad way of performing hypothesis testing. Okay, and if you don't get used to this structure here, you won't be able to realize somebody's actually lying to you. Okay, somebody's actually inserting their own agenda and make it look like a statistic. Okay, now once you stick with this, you can catch people how people, journalists, actually distort the story. They say one thing at the beginning, they claim one thing at the beginning, they conclude another thing at the end. Okay, so you may claim Thomas. I can claim, oh, Thomas is a good teacher, and here's the evidence. Okay, here's the evidence. Conclusion. So you should take Thomas' class. No. If the claim is about Thomas is a good teacher, means Thomas is one of your option, but doesn't mean you have to take Thomas' class. Okay. You may have other instructors who are equally good or even better, right? The conclusion should not be that you should take Thomas' class simply because he's a good teacher. Okay. I believe I am a good teacher. Okay. But the structure of my class, which is once a week, is not good. And I think I said that since the very beginning. Okay, if you have the option of choosing a class that runs actually at least twice a week, that would be better. Okay. With me, even though I'm a good teacher, but because this is once a week class, then it will be not that easy to follow. Okay, that's why I use lecture videos, so that if you have time during the weekend, which you're supposed to, then you can make it as if it feels like twice a week class or 3 times a week class. Okay, that's my purpose. Well, anyway, coming back here. We are not talking about Thomas a good teacher or not. I'm talking about hypothesis testing, at least in my class, and later on when you already pass this class and then you transfer to university and you need to do some hypothesis testing on certain claim, then you're supposed to write it in these 6 steps. Okay. And write you even need to write, I even require you to write this 1, claim, 2, hypothesis, 3, test statistic, 4, p-value, 5, informal conclusion, 6, conclusion. If there's anything that you can skip in your formal report, in my class, you need to show me all these 6. Okay. Now, in formal report, if there's anything you want to skip, the only one you can skip is this one. This is the only one you can skip. Okay, so from step 4, your step 5 is the formal conclusion right away. Okay, in the formal setting, okay, when you write a hypothesis testing report outside of my class. Okay, in my class, I still require to write that informal conclusion. Now, that step is actually provided to help you writing a better conclusion in step 6. Okay, now let's start. Today, we will start with hypothesis testing on mu with sigma known. Now, this section, this part, was in our older edition, the 10th edition, even 11th edition, I remember, but suddenly disappeared in the 12th and 13th edition, which is our current edition. Okay, now I still teach this part because first, it provides good foundation for 8.3 and 8.2, okay, especially. And it is actually still being used in real life setting. Okay, so it's not something we don't use at all. Okay, now, before I really start, let me first say the requirement for each. For 1 and 2, hypothesis testing on mu, the requirement is that satisfy the situation satisfies central limit theorem. In other words, either the underlying population is normal. In other words, the sample is obtained from a population that is known to be normal, or otherwise, the sample size is at least 30. Okay, now the requirement for hypothesis testing for population proportion is that the number of success and the number of failures has to be at least 5. That's the old requirement, which is still being used. The newer requirement is that n times p hat, which is the number of successes, times q hat is at least 10. That requirement is actually a lot stricter. But in my class, as long as it satisfies this, we are good enough. Okay, yeah. Most of the time, however, in public, for you to achieve this, actually, all you need to do is to increase your sample size, increase your n. Okay, and the requirement for hypothesis testing for population variance, population standard deviation, the underlying distribution has to be strictly normal. Okay, those are the requirements. Now, when I go over those hypothesis testing, I will remind you of this requirement. Okay, I will remind you on this requirement. Now, let's start with some examples. Hypothesis testing for mu with sigma known. I will do 3 problems, and I picked this question from internet. Okay, so please forgive my wording, which is not mine. Okay, now you can get these questions from the handout that I post on the discussion board. Jim Nation claims that the mean ACT score attained by 2-year college students is 22. Al dente suspects this claim is too low and selects a random sample of 121 2-year college students. So the n is 121. Okay. Now the mean of the sample, the x bar, is 23.3. Population standard deviation is assumed to be 3.3. Test at alpha significance level 5%. Okay, so we are testing Dente's claim. So there are actually 2 people making claim here. Jim make this claim that it is 22. Al dente suspect that 22 is too low, supposed to be higher. Okay, supposed to be higher. Okay, so let's start with step 1, claim. The claim. The mean ACT score is greater than because Dente says that it's too low, right? 22 is too low, it's supposed to be higher. Okay, so that's the claim then. ACT score is greater than 22. I think I should say the mean SAT score. Now, step 2, hypothesis. Always followed by braces, null hypothesis, colon, alternate hypothesis, colon. Now, this question requires us to test the population mean. So the mu, according to the claim, is greater than 22. Greater has no equal sign, so it will go to the alternate hypothesis. That's how we know if a claim goes to the alternate hypothesis or null hypothesis. If it doesn't have equal sign, then it goes to alternate hypothesis. With equal sign, it goes to null hypothesis. Now, by the way, our textbook, just like a lot of recent textbook, change their style when they have null hypothesis, they make it equal. Okay, that's the current one. Now, if that's what you want to do, that's how you learned it before, go for it. That's okay. With me, I still stick with the old school statistic where the null hypothesis and alternate hypothesis supposed to be complementary. They're supposed to complement to each other. Okay, that's based on the knowledge that the hypothesis, the two hypotheses here should be competing. If one of them not right, then the other one has to be right. Okay, now textbook method, just like the recent argument, the reason they make it equal to, they use equal sign, because that's the number, the 22, they will use in step 3 later on. That's their argument. Okay, that's the number they will use in step 3 later on. Okay, but null hypothesis, alternate hypothesis, in my opinion, supposed to be complementary to each other. Okay, but you, again, for the null hypothesis, you can either use this one, which is my style, or you can use the textbook style, okay, which is a more recent style, either one. Now, I teach you both styles here for your null hypothesis, because when you go to university later on, when you transfer to university and you take 400 level class in statistics again, very likely the one teaching you are not those TA or just fresh graduate. No, very likely they are professors who already taught statistics for a long time. Okay, so very likely their teaching style is still old statistic. Very likely they follow mine instead of the newer one. Okay, that's the reason I teach you the old and the new one. The old one, if you go to university, later on you take another statistic class, especially if you're in psychology, right? Then you will do this again and again and again. Very likely you see the old statisticians, like statistician who use old style. Okay, however, when you later on go to work and perform hypothesis testing, then you will see most people actually use the newer style. Okay, but this is just opinion though. Okay, either this one or that one. Each one of the tradition has their own line of thought. Okay, it's not something I strictly enforce. For sure is that the alternate hypothesis should be the one that has no equal sign. Okay, step 3, test statistic. Since the population standard deviation is known, then we will use standard normal distribution, C-score. Okay, the numerator, the sample mean minus the claim mean divided by standard error, 3.3 over square root of 121. Okay, now then use your calculator. Let me show you how I will use my calculator. I do not recommend you to punch all numbers at once. Okay, let me show you first what if I punch all those numbers at once. Okay, if I punch all those numbers at once, then you need to use parentheses on the top for the numerator and denominator. Okay, on the numerator, parentheses, 23.3 minus 22, close parentheses. That's for the numerator. Okay, divided by the denominator, use parentheses again. 3.3 divided by square root of 121, square root of 121, close parentheses. Okay, so the numerator divided by the denominator. Make sure you use parentheses here. Make sure you use parentheses there. and we get 4.33333. Now that's for step 3. Step 4, how about the p-value? If the parameter is greater than a number, then it will be a right tail test. Okay, what is the reason? What is the reason? To say that the mean supposed to be greater than 22, I need to come up with a sample mean that is significantly greater than 22, not just barely greater than 22. Okay, that's why we call this status quo. We call this status quo, and this is the challenging hypothesis. Okay, just to remind you why. For you to say that the mean is greater than 22, you need to come up with an evidence that is significantly greater than 22. Okay, not 22.1 maybe, especially with the sample of 121, 22.1, that's just a small difference, you know, that's may just happen because you happen to choose 3 or 4 more students that happen to have a higher SAT score. Okay, it may happen by sampling bias. Okay, so you need to come up with an evidence, in this case, the sample that has a mean significantly greater than 22. Okay, so we will use right tail test. If the sign, the inequality sign here is less than, then it is left tail. If the inequality sign is not equal to, that's two tail. Now, what is the p-value? You draw the C distribution, standard normal distribution, and put your test statistic. That's a right tail test, which means you need to find the area to the right of that test statistic. Okay, that is the p-value. P-value is normal CDF from 4.33333 up to E9901. Yeah, too bad we don't have that much time. Okay, I can teach you a lot of things about this, how to type it. Okay, I can show you right now. I can show you right now. Okay, so suppose I want to compute this, right? Okay, distribution normal CDF 4.33333, and then the upper we usually use E99, right? Okay, the mean is 0, standard deviation is 1. Boom. That's 7.3 at the 6th decimal place. That's 7.349. Let me see again. Times 10 to the negative 6. But I never want you to write this as your final answer. You need to write it down in decimal. 0.12345 Okay. It means this 7 here, this 7 here is at the 6th decimal place. 1, 2, 3, 4, 5, 6. Which, if I round to 5 decimal places, that's basically 0. Okay, the way we express that we round it to 5 decimal places is by writing it that way. Oh, actually, no, it's supposed to be 1. like that. Okay. Now, what I want to show you is this, though. If you remember, I have said that before. A standard normal distribution have the tail area get smaller and smaller. Okay, such that if you actually get from -10 to the left, the area there is already so small that it is approximately 0. Okay, it's so small, it's already at least 10 decimal places. And if you change this to 10 here, okay, the area here is basically also 0. Okay, now this is not true for other normal distribution. It has to be only standard normal distribution, That is, the mean is 0 and 1. Now, what I meant is this. Suppose I compute this normal CDF again with lower bound 4.3333 and the upper bound, instead of infinity 10 to the 99, I use just upper bound is 10. You will see that the result is exactly the same. You see that? It is exactly the same. Why? The area is so small such that it is already off by, according to what we see there, it is already so small such that the difference is less than 10 to the -14. The area is already less than 10 to the -14. Okay, that's why when I use my calculator and compute it, I want to do it fast. I don't actually use E99. I just use 10, as long as this is 0 and 1. Okay, as long as this is 0 and 1. Okay, and you can replace this E99 here, the infinity. Okay, you can easily replace this by something very big, as long as it is bigger than 10 times the standard deviation above the mean. Okay, this is actually side story. You don't need to know this. But it's nice if you know something more, right? Okay. Okay. The number I use here, can be replaced by any number more than 10 standard deviation above the mean. So let's say the mean is 100, that's the mean, and the standard deviation is 15, right? Okay, then I may just use 100 plus 150, that's 250. That should be good enough. You don't need E99, that's way too big. Okay, now the good news is when you use calculator, you don't feel the difference actually. You don't feel the difference if you use E99 or you replace that by 250, or in this case, I replace that by 10. You won't, how to say that? It's like, if you know it, you can do it fast. If you don't know it, and just stick with that E99. Okay, now that's a side story though. That's the p-value. Now, because the p-value is much lower than alpha, which is 5%, then the informal conclusion will be because the p-value is less than alpha, then the informal conclusion will be reject null hypothesis. Okay, why do we reject null hypothesis? Because this is the storyline. Okay, what is alpha? Alpha is type 1 error. Alpha is type 1 error. That's the probability. This is the probability of rejecting null hypothesis when it is true. Probability of rejecting null hypothesis when it is true. Now, you can also think of that as the risk of rejecting status quo when it is still okay. Now, what is p-value? P-value is the probability to come up with this evidence, probability to come up with that evidence, given the null hypothesis is true. Suppose the null hypothesis is true, the probability that we come up with this sample mean with sample size 121 is this small. It is already smaller than the risk that we are willing to take. So is it possible, Thomas? Don't you think it's still possible that the actual mean of SAT score is only 22 and all of a sudden we come up with a sample mean of 23.3? Is it possible? Yes, it is possible. But the probability is so small such that the probability is so small such that we will not bet on it. Okay? It's so small, it's smaller than the risk that you are willing to take. Right? 5%. Okay, this is much less than 5%. Okay, in other words, while it is still possible that your sample mean is actually 22 and getting this, I'm sorry, your population mean is 22 and getting this sample mean, while it is still possible, okay, it is very, very unlikely such that it is more likely that your population mean is actually greater than what you claimed earlier in the null hypothesis. What the null hypothesis say. Okay, so we are not saying that it is impossible to happen. We are not saying that if the population mean is 22, then it is impossible to get this sample mean. No, we are not saying that. What we are saying that the probability is so small such that it is more likely that the population mean is already greater than 22. Okay, because sample has bias too, right? Sample has its own bias too. But at the same time, sample is our evidence. Is it possible that the evidence you get is actually a biased evidence? It's possible. Okay, is it possible that Thomas is a bad teacher based on the opinion of 3 or 4 students? It's possible, but the sample size is too small, right? People will question that kind of result. But if you can come up with like a sample of 60 students saying Thomas is a bad teacher, okay, out of like 100 students, then very likely people will listen to your opinion. So you see that there's strength in numbers, right? Okay, there's strength in number. Okay, that's the purpose people demonstrate. Okay, I'm not saying that I support demonstration. Okay, some demonstration is justified, some of them are not. But either way, the idea is there's strength in number, and demonstration is basically show off numbers. Okay, if you try to demonstrate and only 20 people show up, you better cancel it. It is embarrassing. Okay. Okay. Now, the informal conclusion reject null hypothesis. Why? Because the probability for us to come up with this sample mean, while this is the population mean, is so small, smaller than our alpha. Okay. Now then, step 6, conclusion. Remember I said that is it possible that we come up with that sample mean of 23.3, while the population mean is actually 22. Yes, that's possible. The probability is so small. But at the same time, because there is still a chance for us to make a wrong conclusion, okay, we will not use the word proof, because the word proof means 100% true. No, we are not 100% true. Okay, we never reach that kind of conclusion. Okay, we never say we prove. In fact, we will not use the word we will not use the word I. What we use is the sample as the evidence. So we are actually comparing with evidence, which is our sample, versus the claim. It's not we or I against the claim. No, no, no. It's the evidence against the claim. And we are the jury. We just administer the statistic laws, the statistic rules. Okay. And think of that in the court of justice. Okay, in the court of justice, it's evidence, a claim against claim is not the judge or the jury against the defendant. No, it's not. The duty of the jury or the judge is to apply the law and weigh the evidence against the claim. Okay, so the conclusion, again, remember, we never use the word I, we never use the word we never use the word proof. Okay, once you use those three, especially if you use any one of those three words, it's a dead sentence. That's it. You lost all of the points. Okay, so never use those. Never use those. Okay, conclusion. At 5% significance level, the one I write in blue is not required. That's my and some people's habit. Okay, we write down the significance level at the conclusion. Okay, and the wording for the conclusion also actually pretty flexible. Okay, all you need to make sure is like you are actually comparing the evidence against the claim. Okay, and does the evidence support, not support, or the evidence sufficient, insufficient to support the claim. Okay, now notice that we reject null hypothesis, right? We reject null hypothesis. Okay, and therefore supporting the alternate hypothesis, which is the claim in this case. Okay, so even though in step 5 we say in step 5 it is reject null hypothesis, doesn't mean we reject the claim, because what? The claim is with the alternate hypothesis. Okay, so there is sufficient evidence to support the claim. But you need to copy paste the claim you make in step 1. You have to copy paste that as is the claim that the average ACT score is higher than, greater than 22. Okay, now I spent approximately half an hour for this one question here, not because it actually take half an hour. Usually it just take like around 5 minutes if you know what to do. Okay, it takes much longer time because I need to explain more details, right? As you get used to this structure and get used to what to do, you should be able to do this in appropriate time. It's approximately 9 minutes. Okay, with some reading, some thinking, using calculator here and there. Okay, now before I let go, I'm done with this. Now, in case you are interested in getting 1 extra point in your test, then do step 4b. That's critical value. Critical value is the number, in this case, the Z critical in right tail, okay, that gives you the region for which we will reject null hypothesis, okay? Because the alpha is 5%, then the tail region is equals to alpha. Now, what is the critical value? The critical value will be, if this is 5%, means the area to the left is 95%, right? Then we use inverse norm, 0.9501, it's standard normal. And that should give you 1.64485. If the test statistic falls on the tail region, this 4.3 something, right? If this is the test statistic, then we reject null hypothesis. Now, the thing is, in the past, I don't teach both p-value and critical value in the same lecture. In the past, a long time ago, when we used a regular calculator, not TI-84, then I told students to just use critical value method. Once we use TI-83, 84, then we just do p-value method. Okay, now starting from this winter, 2021, then I taught my student to learn both, even though in the test, they just need to do either p-value or critical value. But I want p-value. I always want p-value. Okay, you give me critical value, I will penalize you the p-value. Okay, but put it this way. For p-value, for p-value, I usually give 1.5 points, maybe 2 points. For critical value, only 1 point. That's what I say. If you want to earn 1 point extra credit, then give me critical value. What happened, Thomas, if I give you critical value but not p-value? Then I will penalize you 1.5 point, but I add 1 point. So you still lose half a point. Okay? Well, now the thing is, teaching p-value method and critical value method at the same time may be confusing. But let me explain the difference. Let me explain the difference of these two approaches. Okay, they are actually aiming for the same purpose. Do we reject or fail to reject null hypothesis? Now, p-value method is doing such thing from test statistic. From the test statistic, we find the tail area, which is the p-value. And then compare with alpha. Now, critical value method start with alpha and then get the critical value and then compare with test statistic. Okay, now those are the difference of these two approaches. Okay, now the thing is, then if you learn both of these at the same time, you need to be careful to know when to use what. If you use p-value, you find the area of the tail, which means you need to use normal CDF. If you use critical value, means you are finding the C-score, which means you use inverse norm. Okay? So know what they are so that you know how to use your calculator. Okay. Now in our next question, see, anyway, you see that our test statistic is in the tail region, so we still come up with the same conclusion. We reject null hypothesis, right? Okay. The conclusion always need to be the same. Now let's do question number 2. And then after that, we'll do question number 3, and then we take a break. Okay, let's finish this one first. Number 2, does the evidence support the idea that the average lecture consists of 3,000 words if a random sample of lectures of 16 professors has a mean of 3,472 words? So that's the sample mean. Sample mean is 3,472. Given population standard deviation is 500. Use significance level 1%. Assume that the lecture lengths are approximately normally distributed. Why they need to use the assumption of normally distributed? Because the sample is only 16. The sample size is less than 30. So the underlying population, the length of lectures, has to be normally distributed. Okay, now, so what is the claim here? Does the evidence support the idea that the average lecture consists of 3,000 words? The claim. The average lecture consists of 3,000 words. That's the claim. Hypothesis. Null hypothesis, alternate hypothesis, it's about average, so that's mu. Now the claim says that the average is 3,000, so that's actually null hypothesis. That's actually null hypothesis. The claim is here. The claim is there. Now to say that it is not 3,000, to say that it is not 3,000, you need to come up with an evidence that is significantly different from 3,000. And to say significantly different means it is significantly greater than 3,000 or significantly less than 3,000, not around 3,000. Okay, so when we say the claim is 3,000, the mean is 3,000, and you want to refute that, you need to come up with an evidence that is significantly different from 3,000, not simply around 3,000, which can be caused by sampling bias. Okay. It's like this. It's like this. If you want to criticize someone for that person's statement, be reasonable. Okay, be reasonable. Suppose I purchased my T-shirt for $19.99. Okay, and then my wife asked me, Thomas, how much you pay for your T-shirt? And I say $20. Am I lying? Come on. Right? It can go either way, to be honest with you. Depends on how much you don't like Thomas, right? Okay. If you really want to use this against me and say Thomas is lying, okay, then yeah, you can say, no, it's supposed to be $19.99, Thomas, and you corrupt that 1 cent from your wife. Is it right? Okay, but anybody with healthy mind will say, they're just the same. Come on, man. If you want to corrupt, you don't corrupt 1 cent from one person. Okay, I mean, corrupt 1 cent from millions of people. Yes, that's corruption. But to corrupt 1 cent from one person, come on, man. I pay that back for you. Okay, and of course, nobody filed a divorce simply because the husband say $20 while he actually purchased that for $19.99. Right? Okay, but in the court of law, these two numbers are different. In the court of law, of course, these numbers are different, unless we agree at one point that, you know what, as a figure of speech, you say 1999 as 20. Okay, and nobody in their right mind will blame Thomas for saying that $20, right? Okay, now of course we don't say $1.7 million as 2 million. Thomas, I did it by rounding, but yeah, unless you are super rich, 1.7 million is not 2 million. Okay, nobody round to the nearest million unless that person is a billionaire, right? Okay, my house is not even 1 million, so to say that I rounded to the nearest million is a big jump, right? My house is only $530,000, right? Let's say 550,000. I'm sorry, yeah, 550,000, right? By rounding to the nearest million, that will be 1 million. But when people ask me how much is your house, Thomas, I will not answer 1 million. I will say 550. Why? Being reasonable, common sense. Okay. Well, anyway, so we need to come up to refute the claim that the average is 3,000 words. We need to come up with an evidence that is significantly different from 3,000. So you do test statistic. This test statistic is to find how many standard deviation away is our sample from the mean base, how many standard error away from the mean, not standard deviation away, but standard error away from the mean of the sample mean from the claim mean. So suppose this mean of 3,000 is true, okay, how far it is away from that 3,000 in sense of standard error. Okay, now then we will compute that. Let me go back to our normal view. Use your calculator to compute that, please. Okay, what you don't want to happen in your test is you know what to do, but you don't know how to punch the calculator, which I cannot teach you during the test. I cannot teach you that during the test. I get 3.776. That's my z-score. It means if we have standard normal distribution, this is the mu equals to 0. That corresponds to 3,000 words. Then 3,472 correlates to 3.776 in our standard normal distribution. Okay, that's the test statistic. Now, what is the probability that you come up with a sample mean of 3,472 or more extreme? Now, that's the p-value. Okay, that's the p-value. So the p-value is the area to have test statistic 3.776 or more extreme, right? Now, the thing is, this is a two-tailed test. When it is two-tailed test, I need to double that p-value. So p-value is equal to 2 times normal CDF 3.776 to infinity, or you can replace that by 10 in this case, 0, 1, because that's the mean, it's standard normal distribution. Okay, so this is 2 times normal CDF 3.776 to infinity. I get 0.0000798. Yeah, on my calculator, I get 7.97 e negative 5. Right? Means the 7th here is at the 5th decimal place, but 79, it becomes 8. Then multiply that by 2, that's 0.00016. So, informal conclusion, let me point out why we multiply by 2, because it is a two-tailed test. Okay, informal conclusion, we will reject null hypothesis. Why? Because the p-value is less than alpha. Alpha is 1%, as I remember. Yeah, the alpha is 1%, which is already quite strict, but this is still less than that. Okay, conclusion. Conclusion, at 1% significance level, there is sufficient evidence. Or we can say it this way. Another way of saying that the evidence supports, or sample data supports the claim that the average lecture consists of 3,000 words. Oh no, the evidence does not support the claim. The claim is 3,000, but the evidence support otherwise. So it's not. No. I'm sorry. The claim is null hypothesis, not alternate hypothesis. The evidence does not support the claim. That the average lecture consists of 3,000 words. Okay, in my class, this is good enough. If you want to be more professional, then you can see the following. Okay, a more formal wording of conclusion. Okay, if the claim is with alternate hypothesis, okay, then the wording will be support. Okay, Now, if the claim is null hypothesis, then we will try to reject. Okay, basically because null hypothesis already status quo, when we perform hypothesis testing, we try to reject null hypothesis. That's why in step 5, we reject null hypothesis or fail to reject null hypothesis. We never say, actually, we never say we support the null hypothesis. Never, never. Okay, at least that's not the intention. Okay, the null hypothesis status quo already have the benefit of doubt. Okay, such that unless I come up with something very different, then I have to accept the status quo. Okay, so if you want to be more elegant in concluding, I will not give you extra point for this, but something for you, for you to know. Okay, then the wording will be better said this way. There is sufficient evidence to reject the claim that the average lecture consists of 3,000 words. Okay, why? Because the claim is with null hypothesis and the wording of my conclusion is about rejecting that claim. If the claim is the alternate hypothesis, then the wording of the conclusion will be about supporting the claim. Okay. Now, but again, in my test, you can go either one of them. That's totally fine. Now, how about if I want to compute the the critical value? Then you draw the standard normal distribution, two tail. Okay, you have two critical value such that the area of the tails, each of them 0.5%. Why? Because the significance level is 1% being shared by two tail. So the critical value will be plus minus inverse norm 0.99501, which is, as I remember, that's plus minus 2.575 something. A3. Now notice that my test statistic is 3.7. My test statistic is 3.7. It's in the tail, so I still reject null hypothesis. Okay, now let's finish up the third question and then we take a break. After the break, I will come back to the same section here and then teach you how to use calculator to confirm, only to confirm. Calculator is not to substitute the work. Okay, calculator is to confirm. But we do it after the break. Let's do number 3 first for now. Suppose that scores on Scholastic Aptitude Test, that's SAT, form a normal distribution with mean 500 and standard deviation 10. Standard deviation 100. A high school counselor has developed a special course designed to boost SAT score. A random sample of 16 students, so n equals to 16, is selected to take the course and then the SAT. The sample have average score of 544. The significance level, 0.01. Okay. The standard deviation is known to be, population standard deviation is 100. Does the course boost SAT score? So does the course that these 16 students take boost the average to be higher than the claim 500? Okay, so step 1, claim the course boosts SAT scores. Step 2, well, because it is that's boosting means the average is supposed to be higher. So the hypothesis will be null hypothesis, alternate hypothesis, mu is greater than 500. Okay, the null hypothesis is less than equals to 500, or you can use equal sign if you like. This is again a right tail, and that's the claim. Okay, now I usually write that in red, the right tail and the claim. You don't have to, and in your formal report, no, you don't write that one in red, but that gives us the idea. A right tail, this we will use in step 4 when we do p-value. We will use the fact that it is a claim in alternate hypothesis in step 6. Then the wording later on will be, do we support or not support the claim? Okay, if the claim with the null hypothesis, then the wording will be reject or not reject null hypothesis. Okay, so again, the one in red is something you don't need to write. You can, but you don't have to. In your formal report, you don't write that. Okay, that's just your own informations on how to proceed later on. Test statistic. So the test statistic is the sample mean 544 minus 500 over population standard deviation 100 over square root of 16. That's 1.76. That's the test statistic. Now then, step 5, what is the p-value? Standard normal distribution, test statistic 1.76, that's a right tail. So the p-value, normal CDF, 1.76, E99, 0.1. I get 0.03920. Oh, what is the alpha? The alpha is 1%. Okay, so p-value, I'm sorry, informal conclusion. Informal conclusion will be, because p-value is now greater than alpha, right? Then we will fail to reject null hypothesis. In other words, do we support the claim then? The claim is not null hypothesis. The claim is alternate hypothesis. So at 1% significance level, there is insufficient evidence to support the claim that the course boosts the SAT scores. Okay, I don't even have the word the. Okay, now the p-value is 3.9%. So if the significance level were 5%, then we have sufficient evidence, right? There will be sufficient evidence to support that claim. But because the significance level is 1%, then we fail to reject that. How to say this? So this is the work, okay? This is the work. Now, suppose in real life we see the situation. In real life we see the situation, and somebody wants to give you only significance level 1%. If your p-value is less than 1%, then I agree with you. Otherwise, I don't. In my opinion, that's a bit too strict, right? But imagine if you can come up with this. Imagine if you can come up with a sample mean whose p-value is less than 1%. Okay. Now then, the wording in our statistic tradition is the following. Okay, 1% significance level is associated with the word very significant. The word 5% significance level is associated with the word significant. And 10% significant level is associated with the word somewhat significant. Okay, 1% or 2%. Both of them refers to very significant. 5% only significant, 10% somewhat significant. So you don't need to know this again, but in statistic tradition, we may read the conclusion this way. Okay, so somebody may read the conclusion this way. There is no sufficient evidence to support the claim that the course boosts SAT score very significantly, but there is sufficient evidence to support the claim that the course boosts SAT scores significantly. Or in short, we can say the following. Okay, this is just for in real life. Okay, the conclusion is what I write there. Okay, but in real life, the statistician may read the conclusion this way. There is sufficient evidence to support the claim that the course boosts SAT scores significantly, but not very significantly. So the wording that statistician use, significant, but not very significant, actually refers to that, well, the p-value is actually less than 5%, but more than 1%. Okay. Now here I taught you that we have the critical value method, which is the traditional method, right? And then the one I teach you is the p-value method. Okay. The newer, even newer method is called floating p-value. Floating p-value method. Basically, the steps only up to step 4. Okay, they tell you the p-value and you decide your p-value yourself. Okay, depends on at what significance level you want to support or reject it. Now, we don't use that in classroom setting though. Okay, we don't use that in classroom setting. We don't use that in classroom setting. But in practice, sometimes they just come up to the p-value. The statisticians will leave it there. And then the manager, the directors, okay, the CEO will be the one making decision based on that p-value. Okay. In other words, suppose you have a course. Suppose you have a course that give you this result. Will you use this course or not? Okay, because the reason in this situation we reject the claim, we don't support the claim, is because the significance level is too small. If I had used 5% here, then you would support that, right? Okay, so you see the issue right now at hand here is the significance level. In other words, the bias may come from the person who decide 1% instead of 5%. You see what I'm trying to say? Like, imagine if you have a jury. Imagine if you have a jury who, from the very beginning, already do not want to change the course, already have that very strong status quo. Okay, so this jury says that at the beginning, well, let's use 1%. You, as the statistician, needs to know that, hey, if somebody use 1%, means that person really want to keep the status quo. Okay, now, so in practice later on, the more recent one that we say floating p-value, we don't say this. We don't need to say this. You finish at p-value, okay, and let somebody else make the decision, because statistician job is actually not to make decision. It's just to perform hypothesis tests, and this is the p-value. Now, if the p-value is the risk of committing a certain mistake compared to all that alpha. Okay, and that decision should be made by the CEO, okay, the executives, instead of the statisticians. Again, that's the idea, okay? For us here, we still do these 6 steps. Now, I try to expose to you the wording being used in practice. Okay, when they say very significant, it means what? What is the difference between very significant and significant? Okay, now in statistic, the word significant and very significant actually represent certain number. Remember we said we talk about the confidence interval. Okay, confidence interval 95%, 98 or 99%, or 90%. This actually represent 95% represent confidence. 98 or 99% represent very confident. So be very careful when you talk to a statistician. Okay, somewhat confident for 90%. Okay. So if somebody say, are you confident that this is the right guy to marry, right? You cannot say, oh, I'm confident. Okay, quantify your confidence. quantify, give me a number, what percent? And you say, oh, I'm confident at what percent, 70%. No, that's not confident. Okay, at least for statisticians, 70% confidence is not confident. Okay, for statistician, confident is at 95%. Are you confident? Yes. Is it at 95%? Yes. Okay, now we don't use the word confident in statistic for 70%. We don't use confident in statistic for 80%. Are you confident you will pass the class? Yes, I'm confident. At what percent? 60%. No, that's not confident. Okay, when we say confident is 95% in statistic. Okay, when we say very confident means it's 99 or at least 98%. Okay, so the wording that we use in interpretation of confidence interval, then the statistician may say that we are, for example, okay, very confident that the population mean is between let's say 510 to 630, for example. Okay, now when they say it this way, if you pay attention to the word very confident, then you know this is at least 98%. Okay, so is it possible that a statistician don't even tell you the percentage of the confidence level? It's possible, but because they are a lot more professional already, they don't really tell you the percentage. They use the word very confident because they know if you know your stats, you know what very confidence mean. If you don't know your stat, I can tell you 90%, 98% confident, and you still don't know what it means. That's the way they actually discriminate against those who don't know statistics. Okay, now I tell you this so that you know the jargon they use. Okay, the wordings. From the wording, you know what level. Okay, now that's for, will I do this in my statistic class? No, I don't. Okay, I don't. It is a common tradition in statistic education. If I don't tell you the confidence level, then you use 95%. In hypothesis testing, if I don't tell you the significance level, then you use by default 5%. Let me say it again. Significance level, if it is not explicitly said in a question, then we use 5%. Okay? In confidence interval, if the confidence level is not explicitly said, then we use 95% by default. Okay? Just for completeness, let me do 4B, the critical value. It's a right tail, 1%. So critical value is inverse norm, 0.9901. I believe that's 2.32. 635. Okay, now that's the end of this first part that is not in our textbook. Hypothesis testing on mu with sigma known. After the break, we will do hypothesis testing with sigma unknown, and I will use questions from our textbook. Okay, so let's take a break. We come back at 10:05. At 10:05, we will work on the second part from 8.3. Okay, let's start again. To supplement or to confirm our result, we can use our TI-84, actually also TI-83. And to do so, you go to Stat, and then Test, and then C Test. Let's take a look. I believe I mentioned this in my lecture also, but let's see again here. You go to Stat, Test, the first one, C Test. You will enter the data, okay? You will enter the data. Let's take a look on example 1 here. Example 1 here. The mean that we are comparing that with is 22. That's the mu naught. Standard deviation 3.3. The sample mean 23.3. Sample size 121. And the alternate hypothesis, you test mu against mu naught greater than mu naught, greater than 22. Okay, and calculate. Dun. Let me post it somewhere here. Let me post it here. Now, the reason we don't use our calculator only to do this hypothesis testing, not to substitute, but just to supplement our procedure, is because our calculator actually only help us with step 3 and step 4. Okay, our calculator only help us with step 3 and step 4. It doesn't help you with step 1, 2, and 5, 6. No, it's only step 3 and step 4. Even that is, those are without explanation why and how they get this test statistic and p-value. Okay, that's why our calculator is not the substitute for my 6-step hypothesis testing procedure. Okay, it's not a substitute. It's just to supplement, just to confirm if we get the numbers right, especially for test 3 and test 4, steps 3 and step 4. Now let's see step 2. Step 2, we do it again, stats, test, C test. The data is in statistic. The claim mean is 3,000. Population standard deviation 500. Sample mean 3,472. Sample size 16. And we are doing 2-tail tests. Calculate. Dun. Yeah, this way, then you can compare your test statistic and the p-value. Okay, only to get the test statistic and p-value. Question number 3. So your calculator cannot make this decision for you. Your calculator cannot make the decision for you. Okay, that's why you still need to write that 1, 2, 3, 4, 5, 6, because your calculator only give you the result for tests for step 3 and step 4. It doesn't tell you how to get those. Okay, let's see the next one, example test C-test, the statistic is the claim mean is 500. Sample standard deviation is population standard deviation is 100. Sample mean is 544. The sample size still 16. We do a right tail test. Okay, so you see that the test statistic and the p-value. Okay. Do we have to do this Thomas in the test? No, you don't have to. If I were you, I will, just to check if my step 3 and step 4 are correct. Step 1 and 2 are set up. Steps 5 and 6 are conclusion. Okay. Our calculator do not make the conclusion. Do not take the conclusion for you. No, they don't. Okay. Now that's for hypothesis testing with mu on mu with sigma known. Now we will go on with hypothesis testing with on mu with sigma unknown. That's 8.4. That's hypothesis testing on population mean with sigma unknown. I hope by this time you already get used to the procedure, step 1, 2, 3, 4, 5, 6. Then we can go on with the variation. Now, since the sigma is unknown, then in our step 3 test statistic, instead of using Z, we will use T. And of course, in step 4, the p-value will be on T distribution. Okay, so the p-value later on, we will use TCDF. Okay, TCDF, lower bound, upper bound, degree of freedom. Okay, that's the variation. How about the step 1, 2, 5, 6? The same. Okay, those are the same question. The same procedure. Okay, let's do problems. I will do number 13 from our textbook 8.4. This is from 8.4, number 13. I think I will do 3 or 4 problems from here and then do the proportion and then do the population standard deviation. Okay, now number 13, course evaluations. The dataset 17 course evaluations in Appendix 6 in our textbook includes data from student evaluations of courses. The summary statistics are 93 for the sample size, X bar 3.91, sample standard deviation 0.53. Use significance level 5% to test the claim that. Oh, okay, we have the claim there. Claim that the population of student course evaluations has a mean equal to 4.00. Hypothesis, null hypothesis, alternate hypothesis, mu equals to 4. Oh, that's equal sign. So that's null hypothesis, the alternate hypothesis not equals to 4.00. So the claim is here, which means in our step 6 later on, we will try to reject. The wording will be we will reject null hypothesis, reject the claim or not. Okay, and from the alternate hypothesis, we see it's a two-tailed test. It means in our step 4, we need to multiply by 2. Two-tailed. Okay, step 3, test statistic. T equals to, we don't use Z anymore. We use T because we don't know the population standard deviation. We will use sample standard deviation in place of population standard deviation. X bar 3.91 minus 4.00 over 0.53 divided by square root of 93. Then use your calculator to compute. 3.91 minus 4, whatever the difference, divided by parenthesis 0.53 divided by square root of 93. I get negative 1.63760. And then the p-value we have T distribution, not standard normal distribution, is T, but the shape is very similar. Okay, negative 1.63760. I need to find the area to the left and then double it because it's a two-tailed test. So p-value is 2 times T CDF, negative E99, negative 1.63760, degree of freedom is 92. 1 less than the sample size. So use our calculator, T CDF, negative E99 to negative 1.63760, degree of freedom 92. I get 0.05246 multiplied by 2. I get 0.10492, which is greater than alpha. Our alpha is 5%, right? Our alpha is 5%. So step 5, informal conclusion. Fail to reject null hypothesis. Okay, so the conclusion is at 5% significance level, there is insufficient evidence to reject the claim that the population of students evaluation has a mean equal to 4.00. Does it mean that the student evals has the mean of 4.00? No, that's not what it means. That's not what the conclusion is saying. The conclusion is just saying that we don't have enough evidence to reject that claim. It doesn't mean it is true. I just don't have enough evidence to say so. Okay. And that's actually what we usually do, right? Does my girlfriend love me? I think so, but I just don't have enough evidence. That's why we keep on dating, right? Now, you don't break up because you don't have that evidence, right? You may have evidence, but that evidence is not sufficient. So what do? You break up? No, you continue dating. And with the request, please provide me more evidence that we can survive the marriage later on. Okay, that's why some people actually date for quite a long time, right? Okay, of course, there could be other reason. But I also tell my friends, especially those youngsters that follow me, those teenage that I have in my Bible study, I told them, oh no, you don't marry somebody after dating for only 1 month. Whatever you call that as love at the first sight, at the first sight make you happy for a couple of days, but getting married is supposed to have that marriage for years, right? So no, I do not support their decision of getting married after just dating for 1 month. I will tell them, okay, you know what, date for a longer time. Of course, I do not support of a couple to date for like so long time either, unless they have very, very reasonable, strong reason, and both of them agree. Okay. And like not dating for 6 years, that's, in my opinion, that's way too long. I mean, by 4th year, they already know their decision. After 4 years, they should already start preparing for marriage, not making that decision. Of course, they still can break up, bro, after that. Okay, but you don't say after 4 years, like say 6 years, oh, we are still dating. We still try to find out if we are a match or one or the other, you know. Now, after 4 years, you already know, supposed to be. Okay, supposed to be. Anyway, that's my suggestion for youngsters. Okay, but what I'm trying to say here in this case, simply because we don't have enough evidence to reject doesn't mean that claim is right. You see, the wording that we have in hypothesis testing is very carefully crafted such that if you have not learned statistic and the importance of saying your conclusion correctly, you may come up with a very different conclusion. Okay, simply because I don't have enough evidence to reject the notion that she loved me enough, doesn't mean we break up. Doesn't mean we get married right away. No, it's neither. It's not either one. It's neither one. Okay, it is actually then what do? Either you gather more evidence, or if you have to make decision right now, make whatever decision you need. Okay, but you just don't have evidence. You don't have enough evidence to reject that claim. Okay, does it mean we have enough evidence to support the claim? Actually, no. No. Okay, the evidence actually show that it's different though. The evidence show it's not 4.0. It's different from 4.0. It's just not far enough. To claim otherwise, that the mean is 4.0 is an overkill. You only do that if you really need to make a decision as a consequence of that. Okay, but the conclusion supposed to be, the conclusion is not that we support the claim. Okay, even though I will not mark you wrong, right? If you say there is sufficient evidence to support the claim, I will not mark you wrong, but technically that's actually not correct. Okay, you are doing hypothesis testing. Since the claim with the null hypothesis, you try to reject that. And at the end, in this case, we don't have enough evidence. Okay, that's for number 13 in this 8.4. Okay, let's do two more things to supplement this. The extra credit part. How to find the the critical value. Now notice that the critical value is not provided by our calculator. That's why, another reason, I switched to p-value because we can use calculator. But it's a two-tail test, each of them 5%. So this is 2.5%. This is 2.5%. We have two critical values that are opposite to each other. So T critical equals to plus minus inverse T. Area to the left of that critical value, this is 95%. So area to the left is 0.975. Degree freedom, 92. Okay, our calculator. Inverse T. Area to the left, 0.975. Degree freedom, 92. I get 1.98609. 1 plus minus 1.98609. Okay, so our test statistic is in between. This is our test statistic. This is 1.99. This is negative 1.99. Our test statistic is negative 1.64 approximately. Okay, so we still come up with the same informal conclusion. That's one. How about supplementing that with calculator? So we go back to our calculator. We will go to stat, test, t-test. Okay, we use data, use stats, and then we compare that to 4.00. The sample mean is 3.91. Sample standard deviation 0.53. Sample size 93. We are doing two-tail. So this is our, should I put it down here or up here? I put it up here. And then you see the test statistic is T, right? And the p-value is 0.10492. Okay, again, therefore, calculator only being used to supplement, to confirm if your test statistic in step 3 and p-value in step 4 are correct. Okay, not to substitute, but to supplement. Maybe I write here, how do you get this? You go to stat, and then test, and then t-test. Okay. Let's do more problem. Let's see number 15. The question is a bit too long, but I think I love Korean barbecue, by the way. I love Korean barbecue. And when we have Korean barbecue, there's a notion that because you have too much meat, you need to have some garlic to reduce your cholesterol. Now, how about testing that claim that cholesterol for garlic for reducing cholesterol. Okay, so I think around 15 years ago, if you go to pharmacies like CVS at that time, not CVS, what do they call it at that time? Or Ralph's, you will have a lot of garlic supplements. But right now, you don't really see garlic supplements anymore. Why? Because they found out that that claim is not supported. Okay, that claim is not supported. Now, I'm not sure that this number here is hypothetical or based on the real informations. Okay, and it doesn't matter. We will just apply the notion. Okay, we will just apply the hypothesis test. Okay, let's see. In a test of the effectiveness of garlic for lowering cholesterol, 49 subjects, so that's the N is 49, were tested with raw garlic. Cholesterol levels were measured before and after treatment. The changes has the mean of, so X bar, the change is 0.4, standard deviation 21. Okay, now use alpha equals to 5% to test the claim that with garlic treatment, the mean change in LDL cholesterol is greater than 0. So claim. The with garlic treatment. With garlic treatment, the mean change in LDL lower density lipid, I think, cholesterol is greater than 0. By the way, statistic is heavily used in not only in social life, social justice, social sciences, but also in medicine. Okay, in medicine, like in this case here, can we say that garlic actually reduce cholesterol? You will see later on the result will be no, it doesn't. There's insufficient evidence to support that. Okay, but the thing is, this treatment here with this garlic treatment, it's not long term, it's short term. So they only have the claim that if you have garlic, maybe in a couple of months, does it show that it reduced your cholesterol? They found out that they don't have sufficient evidence to support that. Okay, but how about long term? Okay, how about long term? The one that I know may be useful in reducing cholesterol is omega-3. Now, this is off topic though, okay? This is off topic, just from my personal knowledge, okay? Omega-3, the fish oil, okay? Does it reduce cholesterol right away? No, it doesn't. You cannot have omega fish oil right now and then the next day your cholesterol reduce. No, it's actually long-term. The way the way fish oil actually working, as far as I know, is it reduce the viscosity of your blood. How to say that? It makes your blood reduce the triglyceride. Okay, reduce triglyceride. I forgot how to write it. Okay, and therefore your blood is not as thick anymore, but not the blood thinner that you take by taking aspirin. No, not that type. Okay, this is like the triglyceride in your blood is being reduced, therefore it's not as thick anymore. such that the cholesterol can go through instead of stuck into your blood vessel. Okay, now how do I know this? First, I have some family members who are doctors beside my friends. Okay, so I have friends who are doctors. I have family members also doctors. And we have, of course, seniors in our family, right? So my family members usually ask me, Thomas, can you send fish oil? Can you send fish oil? And the one who ordered these are doctors. Okay, so I asked them, what is this fish oil for? Because there's no claim whatsoever that it reduces cholesterol. Okay, and these doctors say, no, there's nothing that can reduce your cholesterol down by just having a medicine. There's no way. Temporarily, yes, there are some medicine with big side effect, but the main cause is because the triglyceride is high. So, so in other words, there are some people, especially in my family, I should say, who has high cholesterol, and that's because they don't exercise enough. Okay, and it happens especially to our seniors, right? Like because they are at the older age, they cannot exercise as much as they're supposed to be, yet their organs already not working as efficiently in digesting cholesterol and triglyceride. So what happened is then their blood get thicker. Okay, they have more triglyceride in their blood because they don't exercise a lot. Okay, and because it gets thicker, then cholesterol also being not well digested. It stays in their blood and start clogging the blood vessel. Okay, so fish oil is not a silver bullet. It's a long-term, something that they need to have in very long-term period and slowly reduce the cholesterol. What I know, it takes like around 6 months. Okay, of course, you start seeing the result in 3 months, but the first thing you will see is your triglyceride will get lower. Okay, now what I'm saying here is not a medical advice. Okay, no, it's not a substitute of medical advice, even though I say it's from my family members who are doctors, from my friends who are doctors. Okay, but it has something to do also with the fact that Indonesians, what we eat in Indonesia, we have different diet. So it could be because of that. Okay, it could be because of that. Okay, but I do see in my grandma that her cholesterol is normal. My grandma's cholesterol, my grandpa's cholesterol is normal. Me and my dad and my mom and my brother has much, much worse cholesterol level compared to my grandparents. Why? Because they have fish oil that I send here regularly, routine. And I myself, staying in America with easy access to fish oil, I don't consume fish oil regularly. That's why my cholesterol level is like over the roof. Okay, yeah. So is there an evidence that fish oil reduce cholesterol? Not in short term. In long term, there's not sufficient evidence. Okay, it works for some people, it doesn't work for other people. So there are some people have a situation where they have high cholesterol, maybe genetic, I don't know. Okay, maybe something else. Okay, now this is site informations though, site informations. I can tell you more that I actually send fish oil to Indonesia to sell also. So with these informations, I tried, well, I have those information from doctors, right? Okay, and then I tried on my grandparents and it works. So their friends ask my grandparents, hey, what did you do? How can your cholesterol level so nice, so healthy? And my grandparents says, oh, because we have fish oil. Where do you get that fish oil? Oh, from my grandson, from my grandchildren in America. So they asked me to send it to them. That's how I sell it. Okay, so I basically, let's say I sell 3 bottles, okay, and the profit from those 3 bottles, I buy my grandma one. Okay, so it's like break even. That's how my grandparents, especially my grandma, helped me. So she knows that, oh, Thomas, you spend a lot of money, which I don't mind at all. You spend a lot of money for my supplements, so let me help you selling. I said, Grandma, enjoy your life. Okay, you can sell for me, it's great, but my pride will be if you are healthy. Okay, that's my pride. It's part, I believe that's part of my duty to take care of her from very far away. You know, a very proud grandson. Okay, hypothesis. Going back to garlic. Hypothesis, that's the claim, and we want to say that it's greater than 0. So the mean change, mu is greater than 0. So this is less than equals to 0. The claim is here, and this is strike tail. Okay, let's see. Step 3, test statistic. By the way, it is test statistic, not test statistics. No, without S. Okay, it's test statistic. That's T equals to X bar, which is 0.4 minus 0 over sample standard deviation 21 over square root of sample size 49. I believe this number is very small. So it's 0.1333. Okay, then what is the p-value? The t distribution has test statistic 0.13, so it's very close to the mean. So the p-value is, you know what, let me move a little bit to the left. The p-value is TCDF. It's a rectangle, right? So from 0.13333 to E99, degree of freedom 48. Okay. Let's grab our calculator. TCDF 0.133333, and then upper limit E99. You can change to 10 if you like. 48. 0.44724. 0.44724. Okay, and then step 5, the informal conclusion. Fail to reject null hypothesis. And then step 6, conclusion. At what percent? 5%. At alpha equals to 0.05, there is insufficient evidence to support the claim that with garlic treatment, the mean change, the mean change in LDL cholesterol is greater than 0. Okay, as a supplement, let's see. Oops, not this one. Calculator stat test t-test. We use statistic. The mean is 0. The claim mean is 0. The sample mean is 0.4. Sample standard deviation is 21. Sample size 49. And we will do right tail test. Calculate. Ding. Okay, so you see that my t score, my test statistic, and my p value are the same, right? Now, how about the extra 1 points, this critical value? It's a right tail, I need 5%. That's the alpha. So this is T critical, which is inverse T, area to the left, 0.95, degree freedom 48. One 1.67722. 1.67722. Now the test statistic is well in the body, not on the tail, right? Which is 0.13. That's why we failed to reject null hypothesis. Okay. Now let's do more problem. Let's do more problem. So far in the last two questions we have, they give us the sample mean and sample standard deviation. Let's find a question where those are not given, but they give us the data. Let's say number 21. Let's say number 21. Listed below are the lead concentration in micrograms per gram measured in different Ayurveda medicines. It is a traditional medical system commonly used in India. Okay, the lead concentration listed here are from medicines manufactured in the United States. So even though that traditional medical system is from India, usually used in India, but the medicines are manufactured in America. Okay, use a 5% significance level. So alpha is 0.05 to test the claim that the mean lead concentration in all such medicines is less than 14 micrograms. Okay, that's the claim, right? But before we start the hypothesis test, we need to first find the sample mean and sample standard deviation. Okay, to find sample mean sample standard deviation, we need to know the sample size, the sum of x, the sum of x squared. Okay, now we will input this to our calculator, which I believe I already show you. I will show you again to remind you. Okay, and to compute that, either manually or just using a calculator. Okay, now let's go back here. How do we input the data? Go to stats, edit. Okay, I already occupied my list 1 here. Let me go to list 2 instead. Okay, my list 2, the second list, the second column, the second group. Okay, the first data is 3.0 or just 3, second data 6.5. The third data 6.0 is just 6, and then 5.5, 20.5, 7.5, 12.0, 20.5, 11.5, 17.5, and this is my data number 10. Okay, make sure I don't skip any data, and then you go to stat, calculate one var stats. And we're working on list 2. Change that to list 2, calculate. This is what I get. Okay, so from there we see the n is 10. The sum of x is 110.5 on the second line. On the third line, we get 1596.75. Now then, from there, you compute what is the sample mean. Now, according to our calculator, it should be 11.05. Okay, but if you need to show computation, that is from the sum of the data divided by the sample size. That's how we get that. Now, sometimes I say it in my problem, if I give you raw data like that, just use your calculator feature to find the sample mean and sample standard deviation. If I say use your calculator feature, just quote that right away. You know that the sample mean is this, sample standard deviation is this, right? Okay, but if I say show your computation, then at least you can get these 3 numbers from your calculator. Okay, and then use those to compute. So sample variance will be 10 times 1596.75 minus 110.5 over 10 times 9. Long time no see, but you still need to know how to do that. 10 times 1596.75 minus 110.5 squared divided by 90. I get this is 41.74722. So my sample standard deviation will be square root of this number put it under square root, I get 6.46121, which is a match to my calculator result. Okay, so you can use your calculator to get this, at least using your calculator to get this. And even though I may need you to show me the work here, you still have something to confirm that. Okay, now, so at this point, we are done with the setup. The setup is n equals to 10. X bar is 11.05. Sample standard deviation 6.46121. Perform hypothesis testing that the mean lead concentration for all such medicine is less than 14 micrograms per gram. So claim the mean lead concentration in all such medicines is less than 14 micrograms per gram. By the way, I have my own opinion on traditional Chinese medicine. Okay, one of my best friend, actually an MD in TCM, traditional Chinese medicine. She graduated from Shanghai. Now, this is what I learned from her. This is what I learned from her. This is what I learned from her. She did say this before. She said that Western medicine has bad side effect on your liver. Okay, the medicine you take makes your liver actually work harder. However, Eastern medicine, especially Chinese medicine, in long run has bad side effect on your kidney. So what she tried to do is to balance those two. Okay, now she herself currently like around 50 years old, but if you see her, you don't believe that she's 50. Very likely you believe that she is 25. She specialized in internal Chinese, traditional Chinese medicine, and for beauty, like not plastic surgery. No. She's not doing that. She is she is practicing traditional Chinese medicine for the purpose of making your face, your body more fresh. Okay, so knowing that even Chinese medicine, Eastern medicine has at times then damaging kidneys, then she actually provides her patients with recipes for improving their quality of life so that they are less dependent on Western and Eastern medicine. You know, if I have a chance later on, I show you her picture. I mean, honestly, when I saw her after many years, I was like, wow, I don't expect you to look younger. And she said that that's what I'm doing. You know, if I don't look younger, I cannot really preach what I'm preaching. You know, I don't deserve to get paid. And she got very good pay. She got very, very good pay. Like as a traditional Chinese medicine, you don't, as a traditional Chinese medicine doctor, you don't expect her to make so much money. But her clients are well-known people in Indonesia. Yeah. Well, anyway, that's the thing. And she also provide me some recipes, health advices for free because we are friends, right? Okay, so at times I don't want to bother her, but she's the one. Hey, Thomas, how are you doing? How's your blood pressure? By the way, she was the one who actually found cysts in my kidney. She was the one who found cysts in my kidney by just holding my hands. It's like a what you call that is a Chinese way to actually see your. Let me see if I have a way to express that. Give me a second. Chinese medicine pulse position. So she was doing this. No diagnosis. Oh, she was doing this to me. She was doing this to me. So I was so surprised when she said this. I said, no, I don't think so. I feel so healthy when she did this to me. And she said, Thomas, yes, if I were you, I will go check. But at least I can tell you one thing. This was in 2011. So 10 years ago, when she did this to me, she said that, Thomas, you have cysts in your kidney, so take care of that. That's the reason you have high blood pressure. I said, well, I know I have high blood pressure, but I really thought that's because of my genetic. It's my parents, right? And then she said, no, in your case, maybe it's because of your parents, like you inherit that genetically, but in your case, you have cysts in your kidney. Go check, go check. I said, oh man, I mean, go see doctor again in America. That's a long line to wait, And she said, but at least I can tell you this, that your ears you have ringing ear. I said, huh? How do you know that? The fact that I have ringing ear was actually known only by my wife and some people very close to me. I mean, she was close to me, but I didn't tell her that yet. We just barely met at that time. Okay, we just barely met for a dinner, and she said, okay, before we do anything, while we wait for our meal, let me check your pulse first. And she said that, yes, you have ringing ear. In fact, it's actually quite bad. I said, wow, you know how to do it. So she performed acupuncture on me right at that restaurant. And I felt better right after that. Seriously, I felt better right after that. Okay, now I'm not saying that traditional Chinese medicine is something I support, but at least on me personally, with her, with other doctor, no, with other traditional Chinese medical doctor, it doesn't work. With her, it works. Okay, maybe it's just friend, such that she knows me so much, right? Okay, and she said, go check your kidney, Thomas. And when I went to check my kidney at Kaiser, then they found out, beside that I have cysts on my kidney, then I have problem with my liver too. So in some sense, she was actually, for some strange reason, out of nowhere, suddenly come back to my life after a long time not meeting her. She's in Indonesia. She's actually helping me a lot to find a lot of trouble without USG ultrasound, without MRI. She found out I have cysts in my kidney. She did say that you may have some issue with your liver, but I'm not sure. You need to check that further. Okay, so even though she's from traditional Chinese medicine background, she actually used Western tools to confirm and then say, oh, go see your doctor. Okay, go see your doctor, confirm that you are actually okay. Hopefully that's the case. But if it is a cyst, you want to make sure that it doesn't change to be a tumor. By the way, I still have that cyst. It's a ping pong size on each one of my kidney. It's not growing after several years of monitoring. So my doctor say, well, we don't need to monitor that anymore unless you start feeling some change of issue. But so far I'm fine. When it comes to my high blood pressure, it's genetic. Okay, I do have fatty liver. It was actually bad at that time. Now I'm getting much better. Okay, but I have congestive heart failure. That's the one that's very concerning. Hypothesis. Null hypothesis, alternate hypothesis. From the claim, mu is less than 14. So that's a left tail claim. So then the null hypothesis will be mu greater or equals to 14, or simply mu equals to 14. Step 3, test statistic. Oh, by the way, I have to remind you again, whatever story I tell you outside of our statistic, okay, like my story about my friend earlier, traditional Chinese medicine, okay, please do not draw any conclusion from there. It's my personal experience, okay, but I'm not trying to tell you that you must be right or not. No, not at all. And in fact, I believe I said earlier that my my experience with traditional Chinese medicine only works with 2 doctors. I have her, she's one of them, and I have another one traditional Chinese medicine doctor in Monterey Park, actually, in Monterey Park, that works very, very well when it comes to some muscle injury. Like if you fall and then you kind of you have bruises here or there, or you sprain, like in my case at the time, I sprained my ankle badly, very, very badly. I fell from the 2nd floor to the first floor, and I landed right on my ankle. So both of my ankle was basically, I thought I crushed it. Okay, so I went to hospital say, oh, you cannot walk for 6 months. I was like, what? I'm a teacher, I need to walk. And then that doctor at that hospital told me, Thomas, you know what? I can confirm there's no fracture, but it's very, very bad sprained ankle. I suggest you to go see this doctor in Monterey Park. It's a traditional Chinese doctor, and ask for his opinion, you know, and the good thing is it's cheap, only $40 per visit. At that time, I think it was $30 per visit. And within 3 days, I start walking. In 3 days. In 3 days, I start driving again to West LA College. So that's amazing. It works well for me. Works well with my mother-in-law. It doesn't work well with my grandma. So I think it has something to do with more than just it works in general. Okay, this is negative 1.4430. That's the test statistic, p-value. That's a left tail. So p-value is TCDF negative E99 negative 1.44380, degree freedom 9. Zero 0.09134. 0.09134. That's the p-value. So from there we see, oh, it's more than 5%, huh? So informal conclusion. Fail to reject null hypothesis. So step 6, conclusion. At 5% significance level, there is insufficient evidence to support the claim that the mean lab concentrations in all such medicine is less than 14 micrograms per gram. Okay. And then using our calculator, let me do the critical value. I need 5% on the left-hand side. That's a left tail. So the T critical equals to inverse T. Area to the left, 0.05, degree freedom 9. No, why I keep on punching that one? It's this one. So inverse T, the area to the left, 0.05, degree freedom 9. Negative 1.83311. Negative 1.83311. My test statistic is not on the tail. This is where my test statistic located. That's why we fail to reject null hypothesis. How about confirming our test statistic and p-value? The mean that is claimed is 14, sample mean 11.05, sample standard deviation is 6.46212, sample size is n. We want to check against less than 14. This is what we get. Okay, so we confirm our test statistic and our p-value. Okay. Now, let me ask you this time, try to do another problem, similar one. Let me ask you to do number 23. Let me ask you to do number 23. I try not to give you a long question again. I want you to use your calculator to find. So part A, let me do part A here. Part A, use calculator feature. Use your calculator feature. To find n, the sum of x, the sum of x squared, the sample mean, and sample standard deviation. So you need to know how to plug in data and where to compute it. Now, after that, then you do hypothesis testing. Okay, do as much as you can. I will give you, let's say, 10 minutes to do this. So part B is hypothesis testing. In which you perform that 6 steps procedure. Okay, I give you 10 minutes to do this. I will be back at 11:25. Then we will cover that. After we're done at 11:25, you know what? 11:25. Let me just give you a long break after that. So we come back instead. Right now it's 10:50. Let's come back at 12 o'clock. That's way too long though. 11:55. Yeah, we come back at 11:55. So 11:55, maybe 11:50. At 11:50, I will start working on this. Okay. record it. 11:55, you can check your work with my work. Okay, then from there, I will go to 8.2. I'm sorry, 8.3. No, this is not 8.4 though. This is 8.3, my bad. This is 8.3. This is not 8.4. This is not 8.4. I have to change it. This is 8.3. Not 8.4. Yeah, so after this, we will do 8.2. Much less time, I hope, at that time. And then we'll do 8.4. Okay, see you later. Okay, let's continue with the lesson. I plug this into my calculator and I get the n is 6, of course. The sum of x is 4,222. Sum of x squared is 3342798. Sample mean 703.66667, and sample standard deviation 272.73333. Now then, hypothesis test, step 1, claim. The sample is from a population with a mean less than 1,000 hit. Hypothesis. The claim is with the alternate hypothesis less than 1,000. So the null hypothesis greater or equals to 1,000. This is the claim. And it is a left tail. Step 3, test statistic. T is equal to x bar 703.66667 minus 1,000 over 272.7333 over square root of 6. What is that? I get T to be negative 2.66145. And then the P value will be that's a T distribution. We have left tail negative 2.66145. So the P value is TCDF negative infinity to negative 2.66145, degree of freedom 5. I get 0.02240340. What is the alpha? 1%. So if we use 1% informal conclusion, fail to reject null hypothesis, and then conclusion. Yeah, this is the case where we have sufficient evidence to support the claim significantly, but not very significantly. Okay, so at 1% significant level, okay, the sample data or there is insufficient evidence to support the claim that the sample is from a population with a mean less than 1,000 hit. So it is the sample mean is less than, but not significantly less than. Okay, and then how about the critical value? That's degree of freedom is 5, left tail. I'm sorry, degree of freedom is 5, left tail 1%. So this is inverse T 0.01, degree of freedom 5. Negative 3.36493. Negative 3.36493. And the test statistic is only negative 2.66. So this is the test statistic here. Okay, that's for this number, number 23, suggested homework. Yeah, try to do more suggested homework. From this 8.3, I suggest you to work on number 13 to number 25, maybe. Okay. Maybe practice one with the given sample standard deviation and the other one with the given data, like the last two examples we did here. Okay. Now then let's go on to 8.2. Now at this point, I think we are good with the structure of hypothesis testing already. Hypothesis testing on population proportion. I just need to give you the template, right? The template. So step 1, the claim still the same. Step 2, the hypothesis will be on proportion. In other words, the null hypothesis, alternate hypothesis will be on P equals to, less than equals to, greater equals to a number, not equals to, greater than, less than a number. Okay, it's not on mu anymore, but it's on P, population proportion. Step 3, the test statistic, we will use standard normal distribution. And the formula is C equals to P hat, the sample proportion, minus the claim proportion over square root of P Q over N. Step 4, P value, just like before. Step 5, informal conclusion, just like before. Step 6, conclusion, just like before. So you see the change is actually with the hypothesis, a very minor change for the hypothesis. For the test statistic, these are the change. Okay, now under what situation we are allowed to use this modeling? When in all time, which I still follow, that the number of successes and the number of failures are at least 5. The newer one is that the sample size times sample proportion P hat times sample proportion of failure Q hat, it has to be at least 10, greater than equals to 10. Okay, we will always check that, but it's actually in real life, if you don't have this being satisfied, then just keep on adding your sample size. Okay, just keep on adding your sample size. Now, if we want to check using calculator, we will use stat, and then test, and then 1 proportion C test. Okay, proportion always C test. Proportion always C test. I will show you that later on. Now, this is the setup. I will work on 2 problems from here, and then I jump to 8.4. Okay, only 2 problems. Why? We already know the structure. Hopefully, at this point, you already learned that. Okay, we will see how to apply this new type of hypothesis into step 2 and step 3. Okay, now let's start. Let me screenshot first. I will do number 9 from 8.2. 8.2, number 9. In a study of the accuracy of fast food drive-through orders, the McDonald's has 33 orders, that's the sample size. Oh no, there are 33 orders that were not accurate among 362 orders. So sample size 362, the number of incorrect orders 33. Okay, significance level 0.05 or 5%. Test the claim that the rate of inaccuracy, inaccurate order is equal to 10%. Step 2, hypothesis. The rate, the proportions, That's the P, right? Now here the P is 10%, so it must be null hypothesis. That's where the claim is. So we will try to reject that later on. The alternate hypothesis, P is not 10%. That will be a two-tailed test. Okay, step 3, I need the P hat. What is P hat? So go back to the drawing board. P hat equals to 33 over 362. That is 0.09116. So the test statistic Z equals to 0.09116 minus 0.10 over square root of 0.1, that's the 10%, the P, times 0.9, that's the Q, over 362. Okay, so then we compute this. I need you to know how to use calculator for this one though. So let's take a look. I will do 0.09116 minus 0.1. You know what? Let me do it this way because that's already rounded, right? So let me do it this way, 33 over 362. So even though what I wrote is only 5 decimal places, but in my calculator, it will take actually more, subtracted by 0.1. Now, this is divided by the square root of 0.1 times 0.9, which is the Q, divided by 362. Yeah, this way I try to avoid as much rounding error as possible. Negative 0.56063. Negative 0.56063. So step 4, p-value. I have the test statistic negative 0.56063. I need to find the area there, but then I need to double it later on because it's two-tailed. So p-value is two times. 2 times normal CDF negative E99 negative 0.5606301. I get 2 times 0.28755. When I multiply by 2, I get 0.57505. It is very much greater than our alpha 5%, so informal conclusion. Failed to reject null hypothesis. And then formal conclusion. At 5% significance level, Yeah, we try to reject null hypothesis, right? Okay, there is insufficient evidence to reject the claim. The rate of inaccurate orders is 10%. Okay, I compared that with my claim, make sure that I don't miss any words. For part 4b, critical value, we have two tails, both of them standard normal, both of them C-score, and we need 5%, that's the alpha, okay, so 5% divided by 2 is 2.5% each tail. 5% means in the middle we have 95%, so this is the critical value whose area to the left is 0.975. So the critical value is plus minus inverse norm of 0.97501. That should be plus minus 1.95996. Okay. And as you can see that the test statistic is actually quite close to the mean. So we fail to reject null hypothesis. Now, how about using calculator to check? Using calculator to check, okay, you go to stat, test, 1 proportion z test, number 5, not number 6, number 5, 1 proportion z test. Okay, and what is the test number? In this case is 10%, I believe, right? So 0.1, sample size 362. I'm sorry, that X is the number of successes. So that's, what's that again? In this case, the number of failures actually, 33. This is 33. The sample size is 362. And we are doing two-tail calculate. Again, this is just to confirm. This is just to confirm. Now, the thing is, I try as much as possible to avoid too much rounding. So my C-score is actually quite accurate. Okay, and then my p-value also quite accurate. Okay, now yesterday I have a case because the sample size is too small, or maybe instead the sample size is too big, such that my p-value is off by 3 decimal places. And don't worry about it. In other words, if when you check, right, when you check using your calculator, you are off in the last 2 digits, then you are fine. Okay, then don't worry about it. Okay, in the last 2 digits. Like for the C-score, if you're off by in the last 2 digits, don't worry about it. Okay, because what? Our calculator does not round. Our calculator actually use all these 10 decimal places. You see what I mean? Our calculator use 10 decimal places to compute the p-value. Okay, so if you see little difference, don't worry about it. Now, if the difference is like 1 or 2 decimal places, then you want to check your work. Okay. at the first or second decimal place, like you instead of 0.575, you get 0.58, then question mark. Okay. Then check your computation again, just in case you punch anything wrong. That's for number 9. Let's do one more question from here. Number 23, is it a good one? Cell phone and cancer. Okay, yeah, let's do it. I somehow think I did that problem before. In my lecture. Yeah, maybe not that one. I think I did this one problem before. Number 25. Let's do number 25. I like that kind of question. It's very short. It's very short. So that we don't spend too much time in reading, and we can attack the problem right away. Number 25. Through a sample of the first 49 Super Bowls, 28 of them were won by teams in the National Football Conference. So n equals to 49, won by teams in NFC 28. Significance level 5%. Okay, so step 1. Test the claim that the probability or the proportion of an NFC team Super Bowl win is greater than 1/2 or 50%. Hypothesis. Null hypothesis, alternate hypothesis, P is greater than 1/2. P is less than equals to 1/2. So this is the claim, and that's right tail. Step 3, test statistic. Z is equal to P hat minus P. Oh, you know what? What is my P hat? What is my P hat? So P hat will be 28 over 49. That's 4 over 7 divided by 7, right? That's 0.57143. So this is 0.57143 minus 0.5 over square root of P, which is 0.5. The Q is also 0.5. Over square root of 49. Huh? Hold on. Why do I get this number? I get 1. I get exactly 1. Let me check again. It's 1. I get 1. Okay, that's strange, nice number. I don't expect that. The p-value, it's standard normal distribution. I have the test statistic 1, so the area to the right is the p-value normal CDF 1 E99 0 1. I get 0.15866, definitely greater than 0.5. I'm sorry, yeah, 0.05, I meant, which is the alpha. So informal conclusion. Fail to reject null hypothesis again. But the claim is with the alternate hypothesis. The claim is with the alternate hypothesis. So the conclusion will be about, the wording of the conclusion should be about supporting the claim. Okay, in this case, we do not suppose the claim. At 5% significance level, there is insufficient evidence to support the claim that the probability of an NFC Super Bowl team, Super Bowl win is greater than 1/2. Okay, calculator, do the test to confirm. So go test 1 proportion C test. It's 1/2, that's 0.5. Dx is, what's that? Dx is 28. The n is 49. And we are testing greater than 1/2. So you see that the test statistic is C exactly equals to 1. The p-value is this. Okay, so they are both confirmed, right? Now let's see if we want to do critical value. Critical value. That's a right tail. Alpha is 0.05. That's 5% here. So the area to the left is 95%. I believe that's 10%, 1.5. 64 something. Yeah, 1.64485. Okay, so it's just applying formulas again. It's just applying formulas for your test statistic. Suggested homework from this 8.2 will be from number 9 to number 25, maybe, or 27. To 25 is good enough. Okay, we go on with 8.4. Hypothesis testing on population standard deviation or population mean. The template. Step 1, the claim, just like before. Step 2, hypothesis. It depends on what you are testing. Therefore, you need to be careful. Okay, here you need to be a bit careful. The null hypothesis, alternate hypothesis. You are testing on population variance. Okay, equals to, greater equals to, less than equals to a number. Of course, then the complement will be not equal to, less than, or greater than a number. Now, the thing is sometimes the wording in the claim is on the standard deviation, population standard deviation. So instead of population variance, you use population standard deviation. Okay, now the trouble usually is in step 3 when you do the test statistic. Okay, the test statistic is chi-squared equals to degree of freedom times the sample variance over population variance. So the what usually happens is this. Okay, the number you put here should be the population variance. If you are given the claim, the standard deviation, population standard deviation, don't forget to square it. Okay, don't forget to square it. So this is the one you need to be careful. Now, likewise, the sample standard deviation usually given. Okay, so if the given one is sample standard deviation, make sure you square it to make it sample variance. Make sure you square it to make it sample variance. Okay, that's the very, very common mistake. Now, step 4, the p-value. The p-value, remember that the chi-square distribution is a non-negative skewed to the right discontinuous distribution. So the p-value later on, you will use chi-squared CDF. Lower bound, upper bound, degree of freedom. Okay, the critical value you will use chi-squared inverse. Inverse chi-squared. I think, no, I wrote it almost right earlier. Chi-squared critical equals to inverse chi. Okay, then area to the right. and then the degree of freedom. Step 5, step 6 are the same, informal conclusion. Then conclusion. Okay. Now, let me ask you to copy this down first in case you have not. If you have, then that's great. I need to take 5 minutes, maybe a little break. I need to get some drink. I feel very thirsty. I'll be back at, right now it's 12:37. Give me like around 7-8 minutes to get some drink. Okay, just a very little break. I'll be back in 5 minutes. I will work on maybe number 9 from 8.4. Number 9, a random sample of 20 aluminum cola cans with thickness 0.0109 inch is selected, and the axial loads are measured, and standard deviation is 18.6 pounds. So the sample size is 20. Okay, from there, they find out that the standard deviation, so it must be sample standard deviation, is 18.6. Okay, notice that this is standard deviation. Now, the axial load is the pressure applied to the top that causes the can to crush. Now, use a 0.05 significance level, so alpha is 0.05. To test the claim that cans with this thickness have axial loads with the same standard deviation as the axial loads of cans that are 0.01111 in inch thicks. Now, the thicker can, which is 0.111, 0.0111, have axial loads with standard deviation 27.8 pounds. Does the thickness of the cans appear to affect the variation of the axial loads? So what is the claim actually? The claim that we want is that cans with this thickness have axial loads with the same standard deviation as axial loads of the cans that are 0.0111 inch thick, which is 27.8 pounds. Okay, so the claim is rather long, huh? So claim cans with 0.0109 inch thick have axial loads with the same standard deviation as the axial loads of cans that are 0.0111 inch thick. That is 27.8 pounds. Okay, hypothesis. The null hypothesis, alternate hypothesis, population standard deviation is equal to 27.8 pounds. Population standard deviation is not equals 27.8. The claim is with the null hypothesis. And the test will be a two-tailed. Therefore, the p-value later on should be multiplied by 2. Step 3. Test statistic. Chi-squared equals to, sample size is 20, so degree of freedom is 19. Sample variance is 18.6. Don't forget to square it because that's the variance over population variance is 27.8 squared. Don't forget to square them. Okay, because both of them given as standard deviation. I get 8.50531. Now the p-value now remember, sometime in the past, I taught you that for chi-square distribution, the peak is approximately at the sample size. That's the peak. Degree of freedom, sample size. Okay, which is either 19 or 20. Now, then from here we see that the test statistic is 8.5 something. The p-value will be the area to the left, but then you need to double it. Okay, because it's two-tailed, right? Okay, so p-value will be 2 times chi-squared CDF, lower bound 0, upper bound 8.50531, degree freedom 19. Okay, so distribution chi-squared CDF. Lower bound 0, upper bound 8.50531, degree freedom 19. I get 2 times 0.019175 multiplied by 2, 0.03835, 0.03835, which is less than alpha 5%. So informal conclusion, that will be reject null hypothesis. Okay, so conclusion, at 5% significance level, there is sufficient evidence to reject the claim that, okay, let me copy paste the claim. That's how lazy I am. Because the claim is way too long. After all, I need to copy paste that as is, right? So let me do this. Okay, that's the conclusion. Now, how about the critical value? It's 5%. So 2.5 here and 2.5 here. We have two critical value, chi-squared critical right and chi-squared critical left. Chi-squared critical right is inverse chi, the area to the right, 0.025. Degree of freedom 19. And chi-squared critical left, inverse chi, the area to the right, 0.975, degree of freedom 19. Okay, then I think we don't have this. We programmed this one though. So inverse chi, area to the right, 0.025, degree of freedom 19. 32.85233, 32.85233. And then what happened to chi-squared left? Chi-squared critical left. The area to the right is 0.975, degree of freedom 19. 8.90652. That's 8.90652. So you notice that the test statistic is 8.5 something, right? Slightly less than that. This is the test statistic. But it is on the tail anyway, right? Because it's on the tail region, we reject null hypothesis. Okay. Now, unfortunately, there is no way for us to confirm our answer using calculator. There is no such thing on our calculator. Okay, there's no such thing on our calculator. Just like confidence interval for population variance, population standard deviation, we don't have that on our calculator. Likewise, right now, we don't have hypothesis tests for population variance or population standard deviation. Okay. Now I will do one more problem. Let's see what problem is good. Let's do number 11. Should I do number 11? I really want to do that one because it's short. But I guess I need to do the longer one. Let's do number 15. Yeah, if they don't give us the population variance or population standard deviation, they don't give us the sample standard deviation, they give us the raw data instead. So what do? Well, you will see that we plug in the data into calculator to get those numbers. Okay, listed below are drive-through service times recorded at McDonald's during dinner times, assuming that the dinner times at Wendy's have standard deviation this. So the standard deviation at Wendy's is population standard deviation. Okay, now this sample is from McDonald's. The sample is from McDonald's. Now, use 1% significance level to test the claim that, let me give some space, the claim that the surface times the, I think I don't need to use the surface times at McDonald's have the same variations as surface times at Wendy's. Should McDonald's take action to reduce the variability? Okay, so let's see, step 2, hypothesis. The same variation, so the sigma equals to 55.93. Alternate hypothesis, sigma is not equals to 55.93. Okay, now then step 3, I will do the test statistic, but for us to find test statistic, we need to first find the sample variance, right? We need to first find the sample variance. Chi squared equals to, how many data here? 8. Okay, so 7 times sample variance, which we don't have yet. Let me color that. We will compute that later on. Over population variance, 55.93 squared. Okay, now let's compute that lazy way. Okay, so I plug in these numbers here. Let's see. I already use, oh, okay, I can use list number 3. Just to remind you, let's see. If I want to delete this list here, what I can do, I go to stats, clear list. Okay, I will clear list 1, comma, list 2. Ding. Then you check. See, list 1, list 2 empty already, right? Okay, let's do in list 1 then. 121, 119, 146, 266, 333, 308, 333, 308. Okay, and then stats, calculate one var stats, list 1. Okay, even if I tell you to compute that manually, you can actually still cheat a little bit that you get this guy and this guy from your calculator and use these 2 numbers to compute. Okay, use these 2 numbers to compute. Now, then you get this guy and this guy to use here. Okay, so this is equals to 7 times 96.240398, so maybe 40 squared. Don't forget to square it over 55.93 squared. Okay, 7 times 96.24040 squared over 55.93 squared. I get 20.72637. Now then, the p-value. Oh, by the way, the claim is here, but this is two-tailed, right? So the value I have later on the tail region, I need to multiply it by 2. So I have 20 something. But I need to double it. Okay, so p value equals to 2 times chi squared CDF, lower bound 20.72637, upper bound E99, degree of freedom 7. Chi squared CDF, lower bound 20.72637, upper bound, make it super big number, degree of freedom 7, 0.004197. Multiply that by 2, 0.00839. 0.00839. I think the alpha is 5%, right? Oh, 1%. Oh, okay. The alpha is 1%. Well, this is still less than that. So, informal conclusion. Reject null hypothesis. And then conclusion. At 1% significant level, significant level, there is sufficient evidence to reject. Remember, because the claim is with the null hypothesis. So there's sufficient evidence to reject the claim that the surface times at McDonald's have the same variations as surface times at Wendy's. Okay, we reject the claim. Okay, how about the critical values? It's two-tailed. Alpha is 1%, so each tail is 0.005. So chi-square critical right will be inverse chi Area to the right, 0.005. Degree of freedom, 7. Now, chi-square critical left is inverse chi, 0.995. Degree of freedom, 7. Program inverse chi, area to the right, 0.005. Degree of freedom. I use my emulator here because it's faster. This is 20 point something. 27774. 0.27774. Hold on. Oh yeah, wow, it's a bit off, huh? And see, the test statistic is here. 2.20.72. So it's slightly, this test statistic is here. Slightly outside, slightly to the right of that critical value, right? But that's enough to reject null hypothesis. Enough to reject null hypothesis. 0.995, degree freedom 7. 0. Oh, very small, 0.98926. 0.98926. Let me use blue. Okay, 2 problems is enough. Your suggested homework will be up to number 15. So from what number? Number 5 to number 15. Suggested homework from here. 8.4 from number 5 to number 15. Of course, just do the odd ones. So I finished this hypothesis testing chapter in this one day. Okay. I'm not really trying, it's not because I want to rush, it's because that we still have only one meeting next week, right? Next week I will do chapter 9. I will give you some introduction in the next 5 minutes. But yeah, next week we'll do chapter 9. There are 3 sections on that chapter 9 we will go over. Okay, let me write it down. Let me write it down so that you know what we will do next week. And therefore, I need you to watch the lecture video. Okay, this is Intro to Hypothesis Testing on 2 parameters. Okay, next week, the chapter 9 will have hypothesis testing on 2 parameters. Okay, now the first one I will discuss, as far as I know, that's 9.3 or 9.2. I forgot which section, but basically I will do it in this order. Hypothesis testing on 2 population means. Okay, to be more precise, later on we will test mu1 minus mu2. Okay, independent case. Then after that, I will do hypothesis testing on 2 population mean again. But that will becomes mu d, mu of the difference, because we will be dealing with match pair dependent case. Okay, and the last one will be hypothesis testing on 2 population proportions. That's P1 minus P2. Okay, what will be the difference, Thomas? Very minor, very minor. The difference will be the variations, let me say. happens at step 2. So let's talk about this one here. Okay, at least so that next week we know what we do. It happens at step 2, hypothesis. Instead of comparing the population mean against a certain number, we are comparing two population means. Is equal to, less than equal to, greater equals to another population mean. Okay, now the problem with this hypothesis is we don't have a constant. We won't have a constant. So what we will do, we need to modify this and have a constant on the other side by subtracting both sides by mu2. That's how we get that constant. Okay. And likewise, for the alternate hypothesis, we do likewise. We get a constant. Then from there, you see left tail, right tail thing, or two tail. Okay, now step 3. Step 3, the test statistic. We'll use T statistic, where on the top we have x1 bar minus x2 bar minus mu1 minus mu2. Okay, but this guy here later on will be replaced by 0 over square root of variance from the first sample plus variance from the second sample divided by sample size. Okay, if sigma 1, sigma 2 are known, then use Z instead of t-score. So next week we'll apply this formula. Okay, the calculator work will be a bit heavier. Now, how about the p-value? The p-value depends on the left tail or right tail. Okay, that will be TCDF, lower bound, upper bound, degree of freedom. Now, the thing is, what is the degree of freedom? The degree of freedom that we will use the following. The degree of freedom that we will use will be the smaller degree of freedom of those two samples. Okay, so let's say N1 equals to 31, so the degree of freedom is 30. And N2 is 35, the sample size, so the degree of freedom is 34. Okay, so when we use our degree of freedom, we choose the smaller one. Okay, the smaller of those two degree of freedoms. Now, that's what we will do tomorrow, next week, when we apply hypothesis testing on two population means independent case. Okay. I think I will just do like around 3 examples next week for this. For each section, I will just do 3 examples. So if possible, I strongly suggest you to watch the lecture video, lesson 13. Okay, lesson 13. Okay, that's for today then. See you next week.